What if the clean energy revolution doesn't come from massive solar farms, giant wind turbines, or sprawling battery grids, but from a single, invisible atom? Not a fleet of machines? Not a multi-billion-dollar reactor? Just one atom of platinum, perfectly placed, silently reshaping the future of the planet. This isn't science fiction. This is real, cutting-edge science happening right now in the world's most advanced laboratories. And at the center of it all is platinum, a metal so rare and powerful that it might just hold the key to humanity's energy independence. For years, platinum has been quietly working behind the scenes. It's in the catalytic converters under our cars, turning toxic fumes into less harmful gases. It's used in delicate medical instruments and life-saving cancer drugs. But its most groundbreaking role is in hydrogen fuel cells, devices that convert hydrogen into electricity with only water vapor as a byproduct. A technology once dismissed as futuristic now stands at the front lines of clean power, and platinum is its beating heart. But there's a catch. Platinum is scarce. Mining it is expensive. Using it in bulk isn't sustainable for a planet trying to transition to clean energy. That's where atomic-level science changes everything. Imagine looking at a piece of platinum, not with the naked eye or even a microscope, but with instruments so powerful they can track the behavior of individual atoms. That's exactly what scientists have started doing with scanning tunneling microscopy and atomic resolution imaging. What they found is astonishing. In traditional platinum catalysts, only a small fraction of the atoms, those sitting at the edges, corners, or defect points, are actually participating in chemical reactions. The rest are just sitting there, contributing nothing but cost. This revelation flipped everything we thought we knew about catalysis. If only certain atoms do the work, why not just use those atoms? And so, the age of single-atom catalysis was born. Scientists began designing materials where each platinum atom is isolated and stabilized, often attached to a support material like graphene, carbon nitride, or a transition metal compound. These single atoms are like snipers, precise, powerful, and efficient. With fewer atoms doing more work, the efficiency of platinum skyrocketed. Not only does this drastically reduce the amount of platinum needed, but it also opens the door to tuning the catalyst for specific reactions by changing the environment around each atom. It's like going from a generic screwdriver to a precision laser, the same material, but now guided with atomic accuracy. This is where artificial intelligence and quantum mechanics enter the picture. Using density functional theory, a quantum-based method to simulate electrons and atoms, researchers can model how a single platinum atom will behave in countless different environments. And with AI algorithms trained on thousands of simulations, they can now predict new catalyst designs without lifting a single test tube. It's chemistry supercharged by computation. Laboratories that once took years to discover a new material can now do it in weeks, even days. This is accelerating the development of next-generation fuel cells, hydrogen production systems, and industrial chemical processes with near-zero emissions. And the impact? Monumental. With platinum catalysts optimized at the atomic level, hydrogen fuel cells become dramatically cheaper and more scalable. That means zero-emission cars, buses, and trains that run farther and last longer. Clean hydrogen can power entire neighborhoods, replace fossil fuels in steelmaking and fertilizer production, and even store excess solar and wind energy for use when the sun doesn't shine or the wind doesn't blow. This atomic revolution also reduces our dependence on massive platinum mining operations, which often come with environmental damage and geopolitical risks. Instead of digging up tons of rock to extract a few grams of platinum, we can now use just a few atoms and make them do the work of hundreds. And platinum isn't the only element being reimagined. These same principles apply to other critical catalysts: palladium, rhodium, iridium, even non-precious metals like iron and nickel. The periodic table is being re-engineered from the inside out. But platinum remains the crown jewel. Its unique ability to bond with hydrogen and resist corrosion makes it irreplaceable in many applications, at least for now. And thanks to atomic-level insights, we can now harness its power more intelligently, more sustainably, and more effectively than ever before. We're witnessing the dawn of atomic precision chemistry, where every atom counts, every bond is calculated, and every reaction is orchestrated like a symphony of electrons. This is where quantum physics meets climate science, where AI meets clean energy, where the tiniest building blocks of nature are turned into tools for planetary survival. And it all starts with one atom. This isn't just about platinum. It's about unlocking the hidden potential of matter itself, about taking control at the smallest scale to solve the biggest problems. The energy transition isn't coming from one country or one invention, it's coming from a new way of thinking. Sometimes, less is not a way that sees the invisible, a way that understands that just more, it's everything. The next time you hear someone say it's just one atom, remember this: one atom of platinum might power a vehicle. A billion such atoms, perfectly arranged, might power a city, and the knowledge to arrange them. That's what will power the future. If this blew your mind, share this video. Let others know what's happening behind the scenes of the elements. Comment your thoughts, your questions, your ideas for where atomic-level technology should go next. And most importantly, subscribe to Atomic Domain for weekly deep dives into the science that's shaping tomorrow. Because here, we don't just explain the universe, we engineer it one atom at a time.